So thank you all for coming to our talk, reaching 5 million messaging connections on Kubernetes. So I'm sure that some of you in the audience might be wondering why a 50-year-old audio company and a product development company from Toronto are on stage talking about such a thing. So allow me to demonstrate, and all things going well with conference Wi-Fi and cellular. Alexa, play Lonely Boy by the Black Keys on stage.
Lonely Boy by the Black Keys from Dylan's Spotify, playing on stage.
Alexa, power off stage. Okay, so really simple problem, right? These two devices, I spoke into this one started playing music. They can even see each other, and they're loaded with wireless antennas. So this really is it's a very, very simple problem, right? Well, it turns out it's actually quite difficult. And that's why Dave and I are here today to share the lessons that his team learned the hard way. Bose connected to help us develop a large-scale prototype of a 100% cloud-native solution that supports at least 5 million smart speakers. I'll just take a few short minutes to explain our problem domain, and then Dave will take you through the technical stumbling blocks that his team demolished one by one on the way to proving out a solution. So, to solve this problem, why do you even need the cloud? Well, as we say in New England, you can't get there from here. There simply is no direct interface that exists between these two devices, so it actually takes hundreds of miles of networking to bridge this 3-foot gap right here. So let's start with the Amazon Echo Dot. The actual voice smarts live in Amazon's cloud, not in the device itself. And when I speak, my voice recording is sent up to the Alexa cloud for processing. And once Amazon actually determines what it is that I'm trying to do, then it hands off the instructions to the Bose cloud to handle. And we lovingly refer to our Bose cloud as Galapagos, and this is where the messaging connections come into play. So like any other piece of Wi-Fi connected gear in your home, it's not actually directly exposed on the open internet. So we all have firewalls in place on our home routers, so these devices can initiate messages out of our home, but never ever allow direct, unsolicited messages to come in. So the best solution to solve that problem is to set up a persistent line when the speaker first powers up. And we chose MQTT, and we have a bidirectional WebSocket running from every one of these speakers to the cloud so that it can basically receive these unsolicited messages at any point in time. For even a few thousand products, this solution is obvious, very tenable. Scaling is the crux of the problem. Managing millions of connections through a central broker is a tremendous challenge. So hopefully, at this point, you've got a sense for the problem that we set out to solve. And a couple of years ago, when I looked around for a suitable solution, I actually came up empty. There are some cloud systems out there, some managed services that we could have gone with that scales to hundreds of thousands of connections, but we could not find any that would actually scale to millions. So as we waited for the industry to catch up, we needed to find some smart people to partner with to prove out that this was even possible. And Dave was the leader of these smart people. And Connected's work really helped us prove out that a Kubernetes-based solution could be both cost-effective and reach this tremendous scale of 5 million speakers in the wild, always connected to our cloud. So Dave's going to walk you through what it actually took to solve this sort of a problem.
Thank you, Dylan. So, just to set the stage, where I'm coming from. I'm just a dev, standing in front of a room of cloud engineers, asking you to love me. So, when you work as an app dev in the web, scaling a web app is a pretty solved problem. Load balancing, sessions, you see it every day with massive websites. Messaging is another thing entirely. So this is just as much about the discovery of what does and doesn't work, and how Kubernetes would change how we worked. We iterated quickly. There's lots we could have done, but if it was working, we just ran with it. So, the team. 4 people, 2 teams, makers and breakers. The makers focused on building the system. The breakers were focused on building the test rig. We could move people around teams to get exposure to both sides. We grew together. We found each other's weak points. It was a really good dynamic. So we're going to talk about the stack, then the testing process, and finally our key learnings. So let's get started. So we're going to go from the ground up what our infrastructure looks like. And why are we doing this again? There was no off-the-shelf IoT that gives us the scale and flexibility that we think we can achieve. So, Galapagos. This is a Kubernetes rollout on AWS, not EKS. A small team in the room here at Bose was responsible for this very impressive deployment. It's deployed via Terraform and Ansible, single region, multi-AZ. And each of my team got a full rollout of the stack. Minikube is great, but being able to spin up the full stack was really key. If you are going to build something at scale, you really have to test at scale. The reproducible environment was really handy. We were able to change the compute instances underneath each of the nodes and the resources very easily for us. So our solution model. As mentioned, we used MQTT, which is the dominant communications protocol in IoT. It's lightweight, binary, payload agnostic, persistent WebSocket connections. But what's in the cloud? Have you ever had to describe this to your parents? To them, it's just magic. What we actually used was VernMQ. So this is our kind of end-to-end stack. So on Kubernetes, we had HA Proxy as our ingress and load balancer. We had VernMQ as our message broker. We built our own custom little service, very uncreatively called the listening service, that listens for device status messages, which is what we are simulating. All of the messages coming up from device are then publishing through to Cassandra, which is going to store a shadow version of the device status, the volume, what it's playing, what its firmware version is. So component by component, seems to be a heck of a lot of HTTP ingress examples in Kubernetes, not a lot of TCP. We weren't using the HTTP upgrade. We were just using straight up WebSockets. Are there other people doing TCP ingress? It's very, hey, there you are. A little hard to find examples. So ingress is confusing. So we chose HA Proxy. It's the de facto standard for reverse proxy load balancing. It is rock solid. It used a ridiculously low amount of resources for a ridiculously high number of connections. So TCP load balancing for WebSockets, quite a bit less confusing than the ingress examples that I could find. Message broker, we chose VernMQ. It's a high-performance, open-source, distributed MQTT broker built on Erlang OTP. Erlang OTP is used very heavily in telephony originally, a really solid base for clustering and concurrency. It scales vertically and horizontally on commodity hardware. VernMQ really stood out for us. We wanted an open source solution. HiveMQ is proprietary. Mosquito has no clustering. EMQTTD didn't have a good model for recovering after a network partition. So VernMQ offered us clustering, bridging, which is a way to move messages between multiple clusters of message brokers, which is really key in our future considerations. MQTT5 shared subscriptions. So this is a way you can load balance the flow of messages. Since the listening service actually has to process every single message that comes through the broker, it would then round robin through all the instances of the listening service. It gave us fault tolerance and extremely well-defined net split behavior. You can tell it if you can still register new clients and how to behave during a net split. And time order integrity, which is really important when you're talking with a speaker in your phone. If you are telling it to raise the volume, play, pause, you want those to come in order. Very important. They also had, there are other messaging solutions in Cloud Native. There's NATS, Stomp, WAMP, but they didn't seem to support the array of features that we needed. VernMQ really did it for us. So the glue. This is our listening service. We wrote this little component in Golang. It's only about 100 lines. It subscribes to the VernMQ with a shared subscription to process all of the status messages that we were simulating. And it writes directly to Cassandra. So this little component is super performant and so easy to build. It was incredible. Finally, we have our data store, Cassandra. So Cassandra is a wide column store, a non-relational DB. It's able to scale and maintain high availability without compromising performance. It stores the most recent state of a device to mirror other IoT offerings, a digital duplicate of the device in the cloud. We were focused in this POC on write, not read. But what we needed to know is, can it handle the volume? It did, very easily. So I won't be talking a heck of a lot about Cassandra, but it was a key component of our build. So Cassandra was absolutely performant, fault-tolerant, massively scalable, and extremely stable. So how did we put this all on Kubernetes? All of our images we've custom built for everything. They were all built on Alpine to give us a nice small image. For VernMQ and Cassandra, because they are clustering pieces of software, we used a stateful set. So it would bring up each node in order, give them a name in DNS that is consistent. We used a daemon set for HA proxy to make sure it was delivered to all of our Ingress nodes. We used a deployment for the listening service. And as an aside, we also had Prometheus and Grafana to make sure we had some observability on the cluster. Man, there's a lot of proper nouns in Kubernetes. You app devs, I'm sure you were aware if you're in the room, gets a bit of getting used to. So that's all of the build. Let's take a look at the test rig. So we chose Locust. This is what the other half of the team was building. We needed to customize a rig to simulate different client behaviors, one-to-one, publisher to subscriber, one-to-many, fan-out, gate crashing. So we looked at things like MZBench and JMeter. In fact, VernMQ has its own tests pre-built in MZBench. But they're not very flexible. They're really kind of built for request response, not pub sub. You can do it, but it's not as flexible. We decided not to go with it. We went with Locust. So Locust is a Python-based system. It has a master node, and it can instruct workers to do all kinds of different behaviors based on what you want. So this way, we could simulate all the behaviors we needed. Now, we deployed this to bare EC2 instances. We didn't want our Kubernetes cluster competing for resources. So our high-level architecture, when you get to the end of it, you had Locust on the outside and the deployment of all the workers. They go into HA proxy, which was pointed at our VernMQ cluster. On the other side of that, the listening service has a shared subscription to all of the messages coming through VernMQ, and it then in turn writes that to Cassandra. So, on to testing. We'll go through a number of the issues. This is by no means an exhaustive list. It's always something. It's configuration, networking, resource limits, cluster sizes. Most of these will be on the build side, but there were certainly challenges on the test side. The first hurdle in particular. But this way we can validate the entire throughput. So we're going to spin it up. We're going to make one Locust worker to see how many connections we can get so we can level set what kind of thing we can do with it. So a reminder, we are going for 5 million persistent concurrent connections, all at the same time. Other platforms support tens, even hundreds of thousands of clients and devices. But we need millions. 5 million, all at once. That's a different kettle of fish. So, obviously, let's kick the tires. How many connections can I get with one worker?
What are the resources for that worker?
What?
Memory, CPU?
Memory CPU, I'd have to go back and look. But there's, we did a lot of component level testing around it just to see what we needed. I think we got about 10,000 at one point per worker. But, so let's run the tests. Let's take a look at the first result. Damn it. That was unexpected, a little underwhelming. So underneath the hood, we're using Python, and we ran into a problem with Python file descriptor limits. The Pahu MQTT client in Python is what we were using for our clients. So underneath that, it's using Python and the select system call. So this is what, everything is a file descriptor. So when you open a socket, that's a file descriptor. Each connection requires one for the MQTT broker and 2 sockets connected to each other. So 3 file descriptors per connected, 1,024 divided by 3, rounded down, that's 340. So why did it block at that? So the workaround. We replaced the select call. We tried using a library called async.io. This was an utter failure. This did not play well with the Locust concurrency model. We had 2 different concurrency models fighting with one another. So we rebuilt Python. There's a nice little constant called fdsetSize that's hard-coded into Python. You can have 1,024 file descriptors, and that's it. Did not expect to begin this by recompiling the Python, but there you go. All right, so let's get on to the next test. 700,000 connections. Well, that's a bit better. So what's the problem? Configuration defaults and network address translation. So we ran into an HA proxy port exhaustion problem. We ran into just a basic configuration limit that was the default in VernMQ. And the service abstraction. We had VernMQ behind a service object in Kubernetes. And that's just another place where you have a NAT issue. So if you're not familiar with NAT issues, for anyone that's new to this sort of stuff, you basically have a tuple of source IP and port, destination IP and port, and your protocol. You only have so many combinations that, of those. We did not properly configure everything. HA proxy, I think, by default starts at port 30,000, so we had to fix that. So our workaround, reconfigure everything. So fix the max connection setting in VernMQ and add 3 more listeners. It's trivial to add more listeners for VernMQ. So we had 4 listeners on different ports. We bypassed the Kubernetes service. Instead of pointing HA proxy at the service, we had it pointed at each individual VernMQ instance, and we would round robin through them. HA proxy, so we had it round robining. We had to increase the number of source ports. That was my fault. We had to vertically scale the Ingress nodes. We ran into a problem. AWS doesn't necessarily tell you exactly how much bandwidth and how many IOPS you get, but we ran into an issue, and as soon as we kicked up the instance size, it was working great. So I even created a little Ruby Sinatra app that would query the Kubernetes API, and it would return templated config for HA proxy and Prometheus and Grafana. As a little interlude, considering all these problems, discoverability, configuration, I really should have thought of something like a service mesh. Do you know where I can find a talk about that? It could be really helpful. So our next result, 1.1 million. Okay, we breached the million. This is good. Our subscriptions fell off a cliff. So whenever you create a connection to the broker, it would immediately subscribe to a unique subscription for its device. You know, something like device / and the ID of the device. The VernMQ nodes were being terminated by Kubernetes. Kubernetes very helpfully brought them right back up. And as it was transferring all the session information, it blew up another node. And so we had this beautiful flap, flap, flap of nodes going up and down. This one was harder to figure out. So we had to do a little more digging. We scaled VernMQ incrementally. We went from 10, 15, 20, 40, 80 nodes. Now, as a point of comparison, some of the biggest Erlang OTP clusters are about 200 nodes. So we were already at about 40% of the largest nodes. But it didn't make a difference. We made these huge clusters, and it made absolutely no difference. We still pitched off a cliff at 1.1 million connections. We're running into some kind of resize reallocation problem. Under the hood, VernMQ is using LevelDB for all sorts of metadata and subscriptions. And something was obviously hitting its limit in all the metadata replication. I have to say, Do not wait to set up monitoring. Grafana and Prometheus were absolutely key in figuring this out. Using Stern to tail the logs of all of our running pods were absolutely key in finding all these problems. So, what was our workaround? Exponential backoff. We modified the clients to add a custom behavior. So instead of connecting and then subscribing, we would delay subscriptions. So they would happen at a decaying rate to make sure that we weren't overwhelming the VernMQ server. VernMQ recovered. Oh yeah. So rate limiting may be a really key consideration in this sort of thing, especially if you suddenly hit one of these allocation problems, or if you can figure out how to pre-allocate all of these resources. So the next result, 1.5 million connections. Not quite as big a jump as hoped, but we're getting there. Our problem was the Erlang OTP scheduler. So all of the schedulers went to 100% utilization. Erlang does these lightweight threads. You might call them fibers, but Erlang threads are a thing. It puts a scheduler on each CPU that it has available to it. It automatically looks at how many CPUs it has available, and it puts a scheduler on it. But everything chugged to a halt. Increasing resources didn't help, again. So we took these VernMQ instances, and we really beefed up the amount of resources that it had available. I think we were at about 12 CPUs. So what went wrong? C groups. So in the containerized world, C groups are really key. This is the way Docker and container engines report the amount of resources available to your container. Erlang OTP is not C group aware. It configured itself to use 4 CPUs. It had 12. It just ignored them. So we had to directly configure the number of vCPUs that were available to it. Thankfully, this got us to the next stage. So 1, 2, skip a few, 99, 1000. 4.85 million connections. What was our blocker? Resources again. Starting to get really frustrated. I mean, we got to 4.85 million connections. I mean, we could say we made it to 5 million, but you know, it feels like you're lying to yourself a little. I know, what's 150,000 between friends? But as you can see on our Grafana dashboard, we were so close, but not enough to feel validated. At full scale, these tests took 5 or 6 hours to get going. We had to ramp up all of the connections. We had to run it for a while. We had to ramp down connections. We had a testing budget. We blew through our monthly budget in a day. Sorry. So we were getting ready for demos, some internal demos, and we were getting so close. So we started this running again. We upped the resources. We get ready for our internal demos. We walk up on stage at our company in front of everyone. 5,000,001 active WebSocket connections. Thank God. So 69 millisecond average latency from publisher to subscriber. Now this is important because 250 milliseconds is a magic number in this world. That is below human notice latency. If you hit play on your phone and it starts playing on your speaker in less than a quarter second, it's a relatively imperceptible difference. You don't notice it. If you wait half a second, that half a second is enough for your brain to go, why is that not working? We were publishing about 9,779 messages per second. We had other tests that got as high as 25,000. It depends on the use case. This was just one of 12 scenarios that we ran. We would distribute the clients across different availability zones, different regions. Yes. But we did it. So what were our key learnings? What did we learn through this process? And boy, is it punishing. Mind your dependencies. Kubernetes does not manage dependencies and relationships between workloads. This is by design, but as an app developer, this is not the pattern I'm used to. We brought each service up in order so we could configure HA proxy and Prometheus later. I know you can mitigate this sort of thing with init containers and have a little listener on a particular port, but it was a little confusing when you're looking at a clustered resource. When do you say it is available? Do you wait for one replica? Do you wait for half of them? Do you wait for all of them? So that was something we really have to think about. Experiment with your resource limits. It is hard to figure out what your limits are. You have to try different workloads, different scenarios. Until you push the pace, you cannot estimate. Do component level load tests. You're going to need rate limiting, and there's no way around doing it at scale. Layers really complicate troubleshooting. We had layers of networking, resources, ingress, routing, abstraction on top of abstraction. It's turtles all the way down, man. Mo layers, mo problems. So with all these layers, figuring out where to look is really key. Are you looking right down at your EC2 level? Are you looking at your ingress, your HA proxy, the service level abstraction? Is it throughput through to Cassandra? Is it the broker itself? It's really hard. This is why setting up monitoring early matters so much. And starting at scale is different than organic growth. You break through one wall and you hit another immediately. But you got to get back up and keep going. This doesn't invalidate what you've accomplished. You literally break through one of these walls, 5 minutes later, face on the floor. Effortlessly scaling via Kubernetes is a boring feature, but it is a killer feature. You don't realize how incredible it is to be able to say, double the size of my cluster, just like that. Take pleasure in breaking those walls. And finally, our solution was a lot cheaper. So I can't share numbers. That nice little orange line is a major IoT platform provider. The little blue line is my team. Over time, every year, you're going to expect to add more devices. So costs decreased for our workload initially over time. We were more expensive. You had to have people to build and monitor and keep track of all the resources and handle it. But the major IoT platform, they build based on metrics, not on resources. It can be number of connections, number of messages, how many active connections, how many stored messages, how big is your shadow store. Further, in the middle of this experiment, the cost model changed on the one we were comparing against. So you can't predict these changes. You can't have cost predictability. So you even see at the 2-year mark, there's that, I'm a good Canadian lad, that's a hockey stick. You can't predict those kind of changes. And if you are scaling, your own resources are what determine what scales, not the metrics of what you're doing. So we expected cheaper. We did not expect how much cheaper. So in conclusion, building a messaging service for millions of devices is a unique challenge. The blockers evolve as this solution grows. Deploying these specific components in pursuit of a scaled outcome was only possible through the flexibility of Kubernetes. So thank you to Kubernetes, and thank you for all of you listening. And I'll quickly say thank you very much to my incredible team. No team lead has been as lucky as me. And thank you to the Bose team. The people that built and rolled out that Kubernetes deployment are here. It has been an incredible experience. Any questions? Yeah.
So you weren't able to use the service abstraction in Kubernetes. I'm curious to find how you register instances of the HA proxy daemon set into what could have otherwise been. Where did you have to register it? Was it HA proxy or the message broker?
So register.
Well, so there was obviously using the Kubernetes service object, routing traffic through that API. It didn't work.
No.
So how were you registering whatever instances you could load balance over?
Oh, we were cheating. When we were doing this, all the connections, all of the clients had a list of all of the ingress points of HA proxy, and it was just round robining through.
Okay.
There's, this is not an apples to apples comparison. We were comparing against an IoT platform, but that included all kinds of extra things, including that lovely little DNS at the front that will distribute the load through for you.
Sure. Okay.
Yes, sir.
How many active connections you have per CPU?
How many active connections per CPU? It depends where. At the HA proxy level, trivial. I think we probably had on the order of 300,000 connections going through a single HA proxy instance. I know you can get a lot more than that, but that was using something like 20 megs of RAM. It was ridiculous. And the CPU, I don't think it ever went above 1%. At the VernMQ level, I'd have to go back and check. We had pretty beefy instances, 12 CPUs, probably on the order of 40 gigs of RAM or so. And most of our tests were conducted with 10 replicas. So you can do the math there, 5 million through 10. So about 500,000 there. Yep.
How many HA proxies did you run? How many VernMQ brokers? And do you guys use TLS to talk to the backend?
We did not use TLS for the test. The idea being that if we wanted to use TLS, we would terminate it at the HA proxy level. We were just trying to set a baseline. In terms of number, I mean, we conducted a vast number of tests with varying degrees of, different numbers of HA proxy, different numbers and sizes of VernMQ clusters. So there was, it's not easy to say what. We did a huge number of comparisons of different levels of replicas and what kind of resource limits they had. So at minimum, we had 10 replicas of the broker. I think we only had about 6 Ingress nodes with HA proxy. I'm not entirely sure. I have to look.
So you had, for VernMQ and the 5 million tests, you only had 10 brokers running?
At one point, yeah. We had more on different tests. We tried 15, we tried 20. Other than that one time we scaled up to 80, I don't think we ever went over 20. Okay. A gentleman there?
How did you manage like the inherent amount of like unknown with, I guess with Bose, like the project management, when you're dealing with so much unknown?
How did we deal with so much uncertainty in product management? That's kind of our sweet spot. That's part of the fun. We got to bring order to the chaos. Bose gave us a very simple problem that has a very complex answer, and they trusted us to just go with it. We kept them in the loop the whole time. We had one-on-ones with them every week. But our lovely product manager, Thomas, over here, brought order to the chaos for us.
And we are a research company, so we're well used to hitting our heads against walls repeatedly until breaking through. So it was a pretty standard pattern for us.
Sorry, that gentleman there?
What was your experience with fault tolerance with VernMQ?
We did not do a heck of a lot of tests with fault tolerance, but basically VernMQ is able to, it does have well-defined net split behavior, and it does reconcile eventually after you open up the connection. We didn't do a heck of a lot of tests that. We were focused more on throughput. But as far as we saw, it was able to heal split brain pretty well without losing information.
Are you okay with nodes going down?
Oh yeah, if nodes go down,
You lose data?
you don't necessarily lose data. There are sessions that are on each individual VernMQ node, but we intercepted, the sig term, and VernMQ would then transfer all of its sessions to another node, and then another node would come up and sessions would redistribute. Okay, sorry, I think this gentleman here.
What is the reason of not using AWS?
What was the reason? These gentlemen built a fantastic system for us to work on.
Yeah, the question was, why not use AWS EKS? It actually didn't exist at the time that we started.
No, that's
working on
true.
this.
They announced it in the middle.
Yep. No, we're firmly committed to upstream Kubernetes. We're very, very happy with what we have right now.
This gentleman?
You didn't talk about Cassandra, but are you using a managed Cassandra from Amazon, or are you?
No, we rolled it ourselves.
Okay. And what is your experience like running these stateful applications in production for an extended amount of time? How reliable are they?
Yeah, so our production cluster right now is 340 EC2 nodes, and we are tremendously happy with the uptime, the stability. There's some people who do some incredible work here in the room, keeping the system up and running, but it's Compared honestly to a managed service where you really lose control over your uptime and your performance, it's been a really, really good choice for us.
I'm losing track of all the questions. I'm sorry.
Do you have plans to go multi-region, and how do you see yourselves accomplishing that?
The answer is, as a firm, yes, and we're actively in the process of trying to figure that out. We are across 3 AZs right now in one region, and going multi-region active-active kind of breaks things up and down the stack. So there's no easy answer, unfortunately, to that question, but we're committed to getting there.
So Cassandra, she was running in Kubernetes.
Running in Kubernetes, Cassandra was running in Kubernetes as a stateful set, yes.
Oh, nice. And the load testing part of it, what are the tools you were using, and is any part of the load testing scripts
Sorry, I couldn't quite hear.
What load testing tools were you using, and are any part of that open source?
Well, Locust.io is an open platform, open source. We just deployed that. The client we wrote ourselves is not open source, but it's probably not all that complex. Really, all it needs is, do I subscribe? Do I publish? How often? So it's actually really easy with the Paho MQTT client to build a very simple client to use with Locust. Sorry, that gentleman there?
So we're using persistent volumes and EBS for the Cassandra state. That's one question. And the other is, do you have any issues with Java interacting with the container and the C groups to understand its resources?
So the question was, do we have, well, persistent volumes on EBS? Yes, we did for Cassandra. We used persistent volumes, as well as Prometheus. And did we have any problems with Java interacting with the C groups? Not that we saw. Cassandra, honestly, was one of the easiest parts of the system. It was never our blocker. When we conducted a test that was a little more ambitious in terms of the distribution of the cluster, it fell over, but that's because we forgot to change the network topology settings in Cassandra.
What version of Java?
I'm not sure. Do you recall what version of Java, Scott? We'd have to go look it up. Our report on this ended up being about 118 pages, so there's a lot of stuff to know about it.
Will you open source that report?
Good question. We'll take that back.
Yes, sir.
Did you test with AWS IoT?
Did we, sorry?
AWS IoT.
Yeah, in fact, so the test I ran earlier, so everything Dave was describing today was a proof of concept. This is dating back over a year. What we actually have today, what I demonstrated, is actually running on AWS IoT.
For the concept
for the concept test, and in fact, that was one of the IoT platforms that we compared to the results with. So we checked latency, we checked number of connections, and so forth. AWS IoT and a few others as well, which I won't name.
Oh.
How much research did you look for the Kubernetes master nodes?
The Kubernetes master nodes? How much resource?
No idea.
Yeah.
Two XLs.
M22XLs.
Thanks, Miles.
We probably changed that. We messed with a lot of your settings.
Back to your cost slide. I'm curious to know why those costs were dropping over time.
Oh, the costs are actually per device per year. So basically, that's the beauty of cloud. You know, at worst, you should be getting linear scale, and in fact, we were getting sublinear scale because basically, you know, supporting twice as many clients shouldn't cost twice as much in terms of infrastructure. So that's why the costs were dropping.
True, but the solution has to grow over time, and I'm curious to know more about the maintenance, new development.
Yeah. Absolutely, yeah. In fact, Thomas at the back of the room created a tremendous spreadsheet with more cells than I care to remember, with all of that information. So that was a big piece. Honestly, from my perspective, cost was one of the biggest pieces that was most interesting about this POC, the way that you could truly get to sublinear cost and not bankrupt the company by having, 5, 10 million speakers out in the wild.
All right, I'll come and talk to that.
We still good for time? One more minute.
One more good time.
Sorry?
Elasticsearch, Fluentd, and Cassandra?
Oh, no. No, we were straight up using Prometheus feeding into Grafana. We had to give it a pretty beefy instance. We only have one instance of Prometheus. So it was gathering metrics from a hell of a lot of stuff. Metrics from Cassandra, from VernMQ, from HAProxy. But we didn't have any particular problem with it. Mm-hmm.
Were the clients authenticated?
No, no authentication. We cheated.
All right, thank you all. We'll take the rest of the questions offline.
And if you want a sticker too of VernMQ, come on up.